Oh, what the heck? Weird.
Oh, it was so hard, Connor.
Thomas, did you stay up too late? Your eyes look like they're at half mast, my brother.
You're muted, buddy.
Yes.
I'll keep them open. Oh, everything I can.
Force them open.
Grab some tape.
Yeah, tape them. Tea bags. Lay back with some tea bags. What's all the tricks? The movie stars out there.
Oh, I thought toothpicks,
Yeah.
There you go. There you go.
Let's see. Share a screen. Trying to do this without a mouse. Old guys don't do good without a mouse. But given that the mouse is back at my house, I'm sure hoping I have this site favorited. Yes, I do. Let's try this out. Sign in. Okay, let's see. You're here and I'm here. So I want to show you something kind of cool that pertains to yesterday. So we played around, of course, with how to calculate the deflection of a beam. I mean, ultimately that was, we built that from the ground up, and I'm happy to stay after class and kind of help you cross the finish line there if you spent some more time outside of class and want to check anything. So that would be awesome. But I want to show you, like, and I don't think I've done this with you. I might have done this with Calc 1 and 2. But when I draw house plans, like this is what I do to calc beam. I'm not using that 5 WL to the 4th over 384 EI. As I mentioned, number one, that's not the only calculation I have to make. I also have to calculate the moment on the beam that, we also discussed yesterday. What was it? WL over 2x minus W over 2x squared. And like that was the moment that was on the beam too. And basically that's interesting because the moment on the beam is like how badly it wants to kind of go, and crack in the middle. Because you can calculate that number, then you have to find a beam that's large enough to handle it. And so that's another calculation I have to make. And so if the first time I ever drew a house plan, actually, I turned it in and they said, "Where's your beam calculations?" And I'm like, I don't know of what you are talking. So then I made the calculations. Well, kind of like I showed yesterday, I sort of figured out how to do it and I made all the calculations and I turned them in, and then they said, "What are these?" And I should have thought about that. It's kind of like how many people understand, what I showed you yesterday. And that was just one of a number of calculations I have to make. And so like they didn't know enough math and engineering to, inspect it. And well, what they wanted was what I'm showing you right here, which is a piece of software that just prints off that everything's great. So I want to show you this quickly before we start. Let me see. I think to do a good job of this, I need to show you something else first. So let me show you something. Share a screen, come on. So I'm gonna give you just a quick example of kind of how this works. Because again, I just want you to understand the world that you live in a little bit better. Okay, there we go. So let's call this, can't I write? Is my pencil dead? Let's call this kind of a beam freebie. And let's say that we have a building. Let's say somebody's going to build a shop in their backyard. This is the kind of questions that I get. And we'll say that, why can't I draw? gonna be a problem if I can't draw. Why can't I draw? Can I draw with my finger? No, I cannot. So let's say the building is 40 by, I'll catch up with the drawing in a second. Maybe my pen needs to be charged a little bit. Maybe the building is 40 by 60. And so I'm gonna put a roof on that. And then I'm gonna need a beam. And I'd kind of like to show you just sort of kind of why that works or how that might look. Come on, pen, don't let me down.
Might need to scroll up. I think it isn't actually on like a page where you can write.
I'm writing on my end. Oh, I think maybe. Let me try minimizing that. Do you see anything different now?
No.
No.
What do you see? Don't you see a
There we
blank?
go. I think now it's on an actual screen.
I don't know what I was
There we
doing.
go. We see it.
Earlier, sometimes it bugs out and it goes like down to a page, like a non-page below all the other pages.
Hmm.
I don't know.
I don't know either. Okay, so let's build a shop. Whoa, easy there, pal. Let's just let it be ugly. So this is 40 feet, this is 60 feet. And now let's put a roof on top of the shop. And so notice this is right in the center. So if I come up to here, let's say that's the peak of the roof. Now I'm going to go back and kind of erase a couple of things that you wouldn't be able to see. And boom, boom. And this is going to run back and boom. And so now we got a shop with a roof. Okay, so that's cool, except for it would be nice to get in the shop. Do you agree with that? This is a great shop, but it'd be awesome if you could actually get in the shop. And so let's do something kind of fun over here. Let's put a door in it. I'm gonna get fired from my drawing job if I can't get a door inside there. So boom, now we got a door. Make it 3D. Now, the fact that I just put a door in it creates a problem. Obviously, it solves a problem. Like, hey, we can get into the shop now. Good job, draftsman. But what problem does that create?
It affected the stability of it.
Yeah, like think about all the roof rafters that are up here. And I'm out in Idaho right now and it snows a lot here. And so what's going to happen if there's a bunch of snow on that roof? Thanks to the door.
It's gonna collapse over the door.
It's going to collapse over that door. And so what you do is come in here and you have, some studs or some, boards on the side effectively. And then you put a beam. You put a beam over the top of that. And so that's called a post and beam structure. The beam sits on top of the two posts. And so now all of this load from the snow that's sitting up here coming down sits on the beam. And of course, as we said yesterday, doesn't that beam kind of want to bow down a little bit? So that's why we got to know something about it, because those can bow down enough that the garage door won't open, or, the windows won't open or whatever. And then of course that transfers the weight to the posts. And now if that beam had, like yesterday, 1,400 pounds on it, does it make sense that would put 700 pounds here? And does it make sense that could actually, pierce like a pencil down into the dirt? So you actually got to put a foundation, like a snowshoe effectively, something on the ground, because it might push into the dirt. And so that's kind of the concept. And so now, does it make sense, however, does it make sense that the snow that's kind of on the back side of the house doesn't rest on that beam? Like that beam doesn't carry the entire roof, it carries part of the roof. And so let me draw just a quick side view of it. So if this is the back of the house, on the back of the house or the back of the shop, we actually have a wall. And all the snow that's on the back of the house, is able to kind of sit on that wall. And because in a normal wall, there's studs every 16 inches, there's, plenty of stuff to kind of carry the weight and transfer it out. But what happens on the other side? On the other side, we've got our beam. And so that's hanging on nothing. Does that make sense? So this is a cross section. Do you see, if you will, that that's a cross section through this portion of the house? Do you at least have a feel for it? And so does it make sense the snow that's on the left side is not on our beam, but the snow that is on the right side, the snow that's on the right side is on our beam. And so this turns out to be true. You don't need to know this, but roofs, at least where you live in Medford, are 40 pounds per square foot is how much the roofing, that's accounting for the roofing. They would, because remember, there's weight on the roof even if there's no snow, but the snow, which is called live load, kind of comes and goes a little bit. And so where we live, that's 40 pounds. But I just drew a plan recently where they were, let's see, which house was that? Blah, 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 I forget. Oh no, I don't forget. It was up by it's a friend's house up by Lake of the Woods and up there. But does it make sense it snows more up there? So I had to look it up on a website, and up there it was like 100 pounds per square foot. So you actually have to know where it is. And so I'm in Idaho right now and it snows more here. I would look it up. It would not be 40 pounds per square foot, even though I'm just in a residential, I'm in a neighborhood right now. So you got to know what that weight actually is. But anyway, for where you live, it's 40 pounds per square foot. Well, how much weight's going to be on that beam then? I want you to just give you a second to think about that because it's not obvious at all.
The weight on the beam would be the weight of the roof plus 40 pounds.
Well, the 40 pounds is both roofing and snow, like it's everything. That's the established number in your area.
Oh, I thought it was the weight of the roof, and then the 40 pounds was you had to go 40 pounds over just in case you had a live load of snow.
No, it's actually 25 pounds for the snow and 15 pounds for the roofing. That's where 40 comes from.
Oh,
So engineers call it live load and dead load. The dead load is the roofing because it never moves anywhere. So you got 15 pounds per square foot for the dead load. And then the snow that comes and goes in our area is 25 pounds.
So
But it could be 200 pounds if you're in, a really snowy area like a ski resort. Well, does it make sense? This is 1 foot of the roof right here. So all of that snow is on 1 foot of the beam. Because remember, we're trying to come up with is W, which is pounds per lineal foot. Well, how long is that stripe right there based on the dimensions of the building that I gave you?
should be 30 or 20.
Yeah, it's half of, well, one of these. Which one? Well, notice that dimension is the 40 feet. You agree with that? I don't know if my drawing was good enough for you to see that. Well, this 20 feet over here is on that stud. And so I don't need to worry about that. But on this side over here, I have 20 feet. Notice that's vertically because the snow falls vertically. I don't have to calculate how long it is as a hypotenuse. It's 20 feet there. And so that's 20 feet at 40 pounds per square foot. That's 800 pounds per lineal foot that's going to be on that beam. Again, I'm just showing you this out of interest because it's kind of cool. And so let's say this garage door that you put in here was 16 feet long. And so does it make sense you have a 16-foot beam? So that means L equals 16 feet. And we know that W equals 800 pounds per lineal foot. Like that's 2 of the numbers we needed yesterday, right? And then we also need E and we need I. I'm not going to go into this again, but if this beam was, say, a 4x12, this is the B and this is the D. And I showed you on your sheet yesterday that the I value that we need is B times D cubed over 12. I'm tempted to show you the calculus about where that beautiful formula comes from too, but maybe after class, or I don't know, we'll see. I do have something important I need to teach you today. So there's where the I value comes from. But notice the I value depends on what beam I choose. Does it make sense? I can't just say it's going to be a 4x12 because I don't know if that beam will be strong enough, or maybe it's too strong. So I actually depends on the beam that I choose, but I can calculate that I number. And then remember the E number was pounds per square inch. And by the way, the kind of numbers that you get for that are like 2 million. If you buy a beam, it's 2 million pounds per square inch. Like that will be its elasticity if it's made out of wood. And so remember, that number was just how elastic is the material. Is it steel? Well, then it has a certain E value. If is it wood, it has a certain E value. And so, you know, those are the 4 numbers I need, right? I mean, those are the numbers I need to find the deflection of this beam. And because I've got to know ahead of time, how much is that beam going to deflect? So that's all cool. But as I said, what I'm doing is, well, I'm just cheating. So let's go use that program that I was mentioning earlier. So watch what I do here. So notice that one right there says new roof beam. That one says new floor beam. So I need a new roof beam, right? Mine's a roof. And so let's see here. So there's my roof beam 1. So let's see what it has for loads. What I don't know is if it's going to come with a load on it. Oh, good, it didn't. So this one says uniform linear load. This one says uniform area load. That's like a trapezoidal load. This is a concentrated linear load. That's a point load. I think it's this one that I want, a uniform linear load. So notice this beam is 14 feet long. So I actually need to go back and choose the right length first. So
Doug, with our shed, since it's kind of like a diagonal roof sitting on top, like it is sitting on top, but would there be any like shear that we should worry about on the wood or anything like that?
yeah, that's one of the calculations, because a beam at the end of the wall where it sits on the post, the beam could just go and slice, which is called shear. And so that's another calculation I have to make. And this program's going to make it for us.
Gotcha. Okay.
So let's see. Tributary. So tributary is how much of the roof is attributed to the beam. And notice that number for us was 20. That was 20 feet that was attributed to the beam. And then when I go into load, I could put the area load on it that we just described. So that load goes from 0 to 16 feet. It goes all the way across. And for a dead load, we have 15 pounds. And for a live load, we have 25 pounds. And that's what we just used. And notice I didn't have to even calculate. I didn't even have to calculate 800. Like this will do it for me. Does that make sense? That's how I got 800 a minute ago. As I said, hey, a total of 40 pounds, 15 plus 25, and then times 20. Well, it's going to do that for me because this is meant to be idiot proof, which again, I think is amazing. I'm a math teacher. If anybody should be disappointed with this, it should be me. It's like, I want to do all these calculations. It's really cool. But I can screw up, and this is not a place to do that. There's no such thing as a B in construction. So notice the only choice I have left, I've said how long the beam is. I've said how much of the roof is on it. And then I've said how much the load is in this particular house in the snow area. Now it's time to just choose a product. And all I have to do is just stick a beam on there and I'm ready to go. And so you see this one right here, how it says Versalam LVL, which is laminated veneer lumber. See how it says 2.1 E? That E is E, and that's 2.1 million, 2,100,000 PSI. And notice there's some weaker ones up here. Here's a 1.8 million, 1,800,000 pounds per square inch. That's the E value of this particular beam. And so I don't know, let's pick that badass one right there. So let's see, how wide do I want my beam? Notice I can choose any beam I want. The question is, will I choose a big enough beam? So let's choose one that's not big enough. Now I have enough experience to kind of know what that looks like, whereas I wouldn't think you would. So I'm going to choose a 3.5 by 9.5 inch beam. And it's just going to tell me you failed or you succeeded. What do you notice over there on the right?
It's very red.
Exactly what I was fishing for, Landon. Red. So this is what the inspector wanted. Does that make sense? Like you can see why they would want that. And notice the percentages. Notice the shear, which again, I'm not going to explain all this, but notice it's 77%. Oh yeah, no problem. But notice the moment, which you know how to calculate, 152%. Like that beam is going to go because it wants to rotate, and this beam is not strong enough to resist that rotation in the middle. Remember how we drew the little M yesterday and said internally it's going to resist that? This one won't do it. Notice which one is worse. Which one is the worst one?
Total or max deflection.
Yeah. And you understand that now. Like you could calculate that number. You know how to calculate that number now with the formula that you have. Not only that, to some extent, you may even have been able to build the formula that calculated that, which is really cool, I think. And so notice this beam, and by the way, it's just an interesting thing for you to know, but it turns out, and you might be able to picture this, would it be okay for a beam to, you know, when you snowed on it, for it to bend down 2 inches? Does it make sense? Like that could pinch the door. That's a lot. That's bending a lot. Even if it doesn't break, the door doesn't open now, you know, that kind of a thing. And so it turns out that the maximum deflection is actually 1 inch. That's okay. I don't know, that's an arbitrary number, but it's like engineers or home designers said, well, if it's 1, we're okay. If it's more than 1, not okay. Now, what are my choices? I'm a designer. What are my choices now, since that didn't work?
You can go back and click more widths and depths until you get one with no red.
Yeah, just choose a bigger beam. Now, but understand I have other choices. Remember how length, we said yesterday that there was the W and then it was L to the 4th. Does it make sense I could just choose a shorter beam? But of course that doesn't make sense because the owner is like, dude, I don't want a shorter door. Like I want a 16-foot door. And so, you know, the answer is choose a bigger beam. But what number am I changing? There's a W, an L, an E, and an I. What number am I changing if I go to a bigger beam?
It'd be the W, right?
Not the W, because I'm stuck with how much snow is on that roof. I would have to change the 40-foot width of the building to smaller if I wanted to change W. Does that make sense? And again, the owner's like, dude, I said I wanted a 40-foot wide shop. You can't just make it smaller because your beam doesn't work. What other number can I control? I can control W, I can control L.
Is it E?
I could control E. Couldn't I use steel instead, which maybe gives me a stronger E value, and then maybe this size beam would work. But remember, the I value was the one that had to do with the shape of the beam. And so that's the easiest one to change, is the I value, which is like just choose a bigger beam. That doesn't require any changes of design and so forth. And then I can still use the same material. But yeah, it's E and I that you actually really have control over. And so, yeah, let's go back and, you know, choose a different beam. So all I do, and notice how idiot proof this is. I just go, oh, that didn't work, it's red. So notice that last one was 200%. And now I just chose a 3.5 by 12. And remember, the 3.5 is how wide the beam is. And the 12 is that D that's being cubed. Well, notice it almost made it. It's almost big enough, but it still failed. Notice it only deflects 1.1 inch, but you still failed. And so it's actually deflection that's the hardest one to meet. If you meet deflection, other ones take care of themselves.
So why did the moment fail on this one, but it passed on a smaller beam?
It didn't. It failed on the previous one too.
Oh, it failed too?
Yeah, it was end shear that was 77%, and now it's down to 60.
Gotcha. Okay.
So can you tell that if I go one size bigger, it's probably going to be okay now? So now I'm going to go down to this 14-incher. Like, bam, everything is black. Sweet. So there it is. Now I've chosen the beam and I know it's going to work. There's no place for me to screw up, right? Even though I know what I'm doing, even though I not only understand these formulas, I can make them, you know, good for me, but it's like, even if I knew all that, I could still get it wrong, and that'd be a bummer. And so then what I do is I go up here to this little report. I click on this report. I think I just clicked on that. Guess I didn't. And I get this printable report, which actually lists, you can see down here, the same percentages that we just saw a second ago. And so notice maximum deflection, it's only going to deflect 0.69 inches. I know that before I build it. Isn't that important? Like you can't build it and then go, oops, sorry, the beam's not big enough. Like I already know how it's going to behave. As a designer, I'm really happy because it's, if you will, safely inside of 100%. It's not like there's anything that's 99.2. And so sweet. And then the other thing I'll just mention really quick is, see up here where it says bearing reaction. See how it says 2,500 pounds of dead load. That's the roof, which means it'll always have 2,500 pounds on the post on one side. But then when it snows, you get another 4,000 pounds. So if it's really snowy, I got 6,500 pounds over there. Well, you better have a big enough piece of concrete, to like a snowshoe of concrete, if you will, for that to sit on. And by the way, it's just interesting to know, but dirt is capable of pushing back 1,500 pounds a square foot. That's the calculation for dirt. And so if I had 1 square foot of footing down there, not going to do it, right? I'd need like 4 of those, 4 square feet, in order to kind of accommodate. Well, that's my job. You see what I'm saying? Like, that's why I get paid. That's why I make money at this, because I know how to calculate this stuff. And I have access to this amazing program that really means I don't need to know any of this stuff. I just need to click buttons until I don't see red. So if I turn this in, does it make sense the inspector can feel good about it because he knows he doesn't have to actually check my calculations? And he can also be an idiot and just go, no red, or all the percentages are less than 100. Good job, you passed. And so it kind of protects everybody from stupidity. On a side note, which is really interesting, I used to take students on tours through, there's 2 Boise Cascade plants in the country that make these beams. One of them is in White City. The other one's on the East Coast somewhere. So I used to take tours with students through this plant, and they test beams. Does it make sense? Every beam is not the same strength. We won't go down the road, down the concept of statistics here, but some beams are going to be stronger than others because you just might get a stronger tree. And you might get a better batch of glue that kind of glues all the pieces together. And so when they break them, although it might advertise, if they advertise that it's going to hold 100 pounds, a beam's going to hold 100 pounds, does it make sense they better design some safety into that and it better hold more than 100 pounds? Turns out the right answer to that question when they test it is about double. In other words, these are double as strong as they're advertising them to be. So if it says 99%, I'm not like, ooh, that's close, it's going to break. I don't even care. If it's 99%, I'm fine, because it's twice as strong. Not only that, when it fails, it's not like the whole thing falls down. It just bends a little too much. You see what I'm saying? So there's a safety factor built into this. And doesn't that feel right? Like, aren't you glad when you drive across the bridge that it's like, it just rusted a hair more, and then, down into the lake you went and died. It's like there's a whole bunch of safety factors built into all this stuff. And especially when it's a civil project, which means lots of people are going to cross the bridge. That shop, 2 people, if I screw it up, if you're really unlucky, 1 person dies because they happen to be underneath it when it fails. And so engineers will design in a 50% factor of safety when it's a project just for, like 1 person, but they double it when it's a civil project and lots of people are going to be on it and so forth. But are there failures? Yep. Every year when I teach engineering, I always pull up whatever the latest one was. And, some bridge falls down somewhere and, it's a bummer, costs a lot of money. And if you're unlucky, people die as well. Isn't that kind of cool? Like you're in the middle of sort of figuring out kind of how all that stuff works. It's kind of neat.
It kind of bothers me a bit that like 1 inch is the limit for deflection for a whole bunch of different beams.
Say that one more time.
It kind of bothers me a little bit that 1 inch
Okay.
is like the maximum deflection for a whole bunch of different beams.
Yeah, right. And I will tell you in a residential sense, that's because if it deflects that much, because they're always going to deflect, they deflect under their own weight, if that makes sense. So they're going to deflect some. And the issue is just, will they bounce up and down? It actually does. If you put it in and it was bent and it just stayed bent, then you could kind of build around that and it really wouldn't hurt much. But the problem is when it snows, does it go down and then go back up and go down and go back up? And you're right. That's why I said 1 inch is really kind of arbitrary. Could you, as a rich guy, say, I don't want it to be an inch, like choose a bigger beam because I want that to be a ½ inch? And I could be like, okay, great. It's just going to cost a little more money because I'll just spec a larger beam. And so fine. So yeah, you're right. 1 inch is totally arbitrary. And again, this is a residential application. Maybe that number's different for that Skyway that was at SeaTac that I showed you yesterday. Maybe that deflection could be way more because it doesn't matter if it bends a little bit. By the way, flexibility is kind of important with respect to seismic stuff, isn't it? Don't you want things to bounce because then they won't break? It's like it bent, but it didn't break. Like you actually want it to deflect so it won't fall down. So you kind of like build movement into it. So it's kind of interesting. There's just a lot of stuff to think about around this, but
I feel like that would be the ultimate power move, just to tell your contractor, be like, I don't want that to deflect half an inch, spec a bigger beam. I'd be like,
I know. It's
This
like,
guy,
man,
this guy knows what he's doing and he's smart.
got some standards. Like, do you even know how to calculate that? No, I just push all these buttons.
Yeah, I kind of expect it to be, I don't know, based on like internal stresses, I guess, but I guess probably that just doesn't come to play. Like the beam would flex way more before that even came into play. So
Yeah, and there's a lot to this. And as I've told you guys lots of times, like I'm self-taught in this. The things I understand because I've had to build them slowly and kind of teach myself, because the people that are smart enough to understand this stuff usually can't explain it. And the people that are good teachers don't have any construction experience, so they can't, they don't know it. And so most of the stuff I'd had to teach myself, and it's really hard to find somebody explaining it, what I consider to be for dummies. And let's switch gears now, and let me give you the for dummies spring version. And I just think people, if something is hard, then great, it's hard. But if it doesn't need to be hard, then don't make it hard. And so that's kind of what I want to do. That's the way I teach, and that's what I want to do. That's what I want to do now. And I will say, like, the stuff that I have learned about beams, I literally had to teach it myself. Like I never had anybody explain it to me in the way that I've explained it to you, because I couldn't find anybody that understood it that well. So hard sell. Now, we today are looking at 4.9, which is titled Free Mechanical Vibrations, which is kind of a cool name, Free Mechanical Vibrations. But we're back to what we started this section with, which is springs. And I'm not going to go completely back over what I did in 4.2 when we first started, but I gave you an introduction to, like, why are we trying to solve second order differential equations? And I gave you this formula for springs. And I said, for springs, I said it is M times Y double prime. I'm looking at my notes because I don't have this memorized. B times Y prime plus K times Y equals forces that are kind of exterior to it. Now, this free business, free mechanical, meaning there's no other stuff acting on it, for today, that's going to be 0. In other words, what kind of an equation is this? How's your terminology? What kind of if it's all the second order equal to 0, what do we call that?
Not homogeneous, right?
Yeah,
Or is it? Yeah, it is.
Yeah, it's homogeneous. Good job. So this is a homogeneous second order differential equation. And so let me just throw a couple of things in here. So we said this was mass, which turns out to be measured, and we're going to do this in the metric system because your book assignment will be in the metric system. That's in kilograms, which is kind of interesting. And because today it's not y as a function of x, today it's going to be y as a function of t, because we need to consider our independent variable as time, not location. Yesterday x was a location, today t, our independent variable, will be time. And so for that reason, the unit of this right here will be meters per second squared. Isn't that how acceleration looks? It's a distance. It's a change of velocity, and velocity is meters per second. So then it would be meters per second per second. And so notice that's kilogram meters per second squared as a unit. So that's kind of a crazy unit. And then this y prime, of course, then would be meters per second, because that's speed. And this y then would just be meters, wouldn't it? Does that all make sense? So y is the position. And by the way, I should draw a picture here really quick. And I'm purposely going to draw the spring, if you will, sideways. So we'll say it's like and the reason I say sideways is because, like, think of it as a spring on a car. This isn't just some physics class where some spring is dangling from a ring stand or something. This is like the suspension on a bicycle or the suspension in a car. And so it's the spring that's causing the motion, not gravity. If gravity was involved, it would not be free mechanical because there is an exterior force and it's gravity. So this is like the only thing causing this to move is the spring. Do you see what I'm saying? So, and the reason I drew that dotted is if you took this thing and pulled it out to here, then that's our distance y. In other words, the distance, y is the distance from equilibrium. And so what you've done is you've, taken this spring on a car and you've, pulled it out and now you let go. And of course, you know what that's going to look like. It's going to go come to a stop, right? Now, do you have to pull it out? Notice I'm calling that the positive y direction. And I think that's nice here because you're used to going right being positive. But couldn't you also press the spring in? Isn't that what happens on a car? Like if you hit a speed bump or something, doesn't that compress the spring? And then it responds by going, and does the same thing. It opens back up again. And that's what suspension on a car is for. So that when you hit the speed bump, there is suspension so that you don't just fly up and hit your head on the ceiling. So y is the distance from equilibrium. So just so you understand what y is. And so that's why y is in meters. Does that make sense? And that's why the change of y would be meters per second. And that's why the change of the change would be meters per second per second. So do you understand why those units are what they are? And maybe those units will help us get problems right. That's why I'm kind of explaining it. Now, if you're going to add all these things together and have it be 0, does it make sense? It can't be like, 5 days plus 3 feet plus 9 miles. Notice at least feet and miles are both distances, but you can't add things together that don't have the same units. So think about that. Like these all have to be the same units, don't they? So what does this be? Now I told you this the other day, but unless you're you have a photographic memory, you wouldn't remember what that was. And I don't either. I'm staring at it right now. That's the damping coefficient. Come on, fit, baby. It's close. That's the damping coefficient. And what I told you the other day was that is the kind of friction. That's the friction. In other words, we said that the speed was this right? I'm trying to remember it's off the top of my head. The speed was, the amount of friction was proportionate to the speed. That's what it was. The amount of friction caused would be proportionate to the speed. And as I mentioned, if you stick your hand out the window, the amount of force you feel on your hand is totally proportionate to the speed, right? If you're going really fast, my friend was telling me he has a Harley and he was riding with this guy who's a really good motorcycle rider and they were going 110 and somebody waved at him and he put his hand up to wave and he was going 110 and he said his arm almost like flew off of his body and he's like so lucky not to crash. So that kind of makes sense, I guess is all I'm saying, is that the friction force is proportionate to speed. But now think of the units. Does it make sense? We're stuck with the same units. Well, notice mass times acceleration was kilogram meters per second squared. If that's the case, then what does the damping coefficients units have to be in order for those to end up as the same exact units?
Kilograms per second.
Yeah.
All right, Ben, you teach us now. You've passed the test.
Yeah, that's exactly right, because it's got to be, and notice that's a really weird unit. It's got to be kilograms per second, because then when I multiplied it, it would be kilogram meters per second squared again. And so isn't that a weird unit? So it's like mass per seconds. But if you're going to add them, don't they have to be the same units? And by the way, you physics people, kilogram meters per second squared is a really weird unit. Like that's hard to say. You know that's been renamed? What's a kilogram meter per second?
That's a Newton, right?
Squared. Yeah, it's a Newton. Often abbreviated with an N. So these all have to be Newtons. Okay, well, if that's true, then K here in the language of a physics class is called the spring constant. In other words, how springy is the spring? In other words, can you appreciate that to pull it out to a distance of y, if it's a really strong spring, you might not be able to do that with your muscles. And so, is it really easy to pull? Is it really hard to pull? So we said the other day, again, I'm trying to remember the top of my head, but it was like how hard it is to pull the spring out is proportional to how far you pull it. In other words, you just pull it a little, that wasn't too hard. If you pull it a lot, that was really hard. So the further you pull it, the harder it is to pull that far. What would the unit of that have to be then? So this is, your book will call this the stiffness, but in a physics class, you're going to be told that's the spring constant, but it means the same thing. That kind of makes sense. How stiff is the spring? What would its unit have to be then? Well, it's missing a kilogram, right? So then we got kilograms, and then it's missing a couple of seconds. So I guess it'd be kilograms per second squared. Isn't that a weird unit? But it's not, what you need to understand is that's just designed to set them equal to each other. In other words, if I said, I'm going to erase this, but if I said the force is proportional to the distance, then proportional just means, oh, there's a constant that relates them. Well, force over here is kilogram meters per second squared, newtons. Like that's what force is. Well, if y is only meters, does it make sense then k's unit, which makes no sense whatsoever? That isn't a meaningful unit. The unit then must be whatever's left to make it equal. Like you can't have them be equal if they aren't the same unit. Isn't that interesting? So you just get really weird units. And again, I'm taking a physics class, and that was one of my 2 C's in college as a freshman was physics. And it was because the typical PhD physics instructor at U of O, just said, this is the units of the spring. And how does it make sense to me? Well, that's because it doesn't make sense, but that wasn't explained. And so, I just, hard for me to make sense of. So that's just kind of cool to know. Incidentally, this is just kind of interesting to notice, but I don't think I'll say this actually. Yeah, I am going to say it. That same unit could be described as newtons per meter. Like you could rename kilograms per second squared as newtons per meter. Do you see that? If I replace newtons with kilogram meters per second squared, then wouldn't the meters cancel? So what you would see in a physics textbook is not that the spring stiffness is kilograms per second squared. They would say it's newtons per meter. And you might see that in your book. They'll say the spring constant is 8 newtons per meter. Now, these problems could be made really tricky, right? If they gave you weird units and you had to convert them all yourself, and like you really would have to pay attention to this, which might happen in the real world. But for the most part, hopefully the book assignment, it's almost like you can just ignore the units, like they set you all up. And interestingly, in the same way, because I actually don't remember, the damping coefficient could also be described as newtons per meters per second. That's a weird way to say it too, but.
Do we actually use newtons in real life? Because it seems like with our beam
All the
project,
time.
it's like foot-pounds.
That's because I did it to you in our system. And I did that because when I went into that beam calculation program, it was in our system where force is in pounds, not newtons, and where distances are in feet, not meters. But honestly, the real standard for engineering is metric. You don't see that in engineering because engineering is sort of worldwide. And so the standard is actually newtons. All the forces I see when I send my stuff off to an engineer is newtons. It's never pounds. And
So
so
basically it's all metric until it's time to go out and like be standardized, and then we like convert everything. Is that how it works?
yeah, I mean, really, you just need to be fluent with both of them. That's what it comes down to. But yeah, newtons are not weird. That's super common.
Okay.
Okay. And so, okay, let's get into this. Let's do a problem now. Enough introduction. So it turns out that there are 4 cases. One, let's see, A, B, C, D. Can I use A, B, C, D? Nah, let's use 1, 2, 3, 4. Case one, what is called undamped. Undamped. Undamped is where B is 0. Does that make sense why B would be 0? Well, I did say B was the damping coefficient, didn't I? And this says undamped. So it's like no B. What this means is there is no friction slowing the spring down, which is impossible to create, by the way, because when you pull a spring, it doesn't just bounce forever, right? There is friction based on heat and wind, and it will slow down. And so this is kind of unrealistic. But what this means is like you pulled it back and let it go, and it just went the same exact size for the rest of its life. If you pulled it out to 2 and then let it go, it just went 2, -2, 2, -2, 2, -2, and then just for the rest of your life. Like that's what undamped would look like. But then there is also, and we're going to look at one example and change just B for every one of these. There's also underdamped, which is when R is a complex number. Remember that? Remember when we solved these and we got a negative under the square root sign? Because remember we had that auxiliary equation, and sometimes to get our R values, and again, we'll do an example again. I know it's been a couple of days. You get a complex number for that. And you know, again, we said that was kind of interesting, but it basically would mean like B squared would be less than 4mk in the quadratic formula. Notice in our quadratic formula, we have not A's, B's, and C's. We have M's, B's, and K's. And so if that B squared less than 4mk is just saying you're going to get a negative under the square root sign, right? So I could have just left it at R is complex. That's underdamped. We'll look at what underdamped means in a little bit. And then perhaps predictably, there's the reverse of that, which is overdamped. And that is where R is actually, remember there were 2 R's because this is a second order differential equation. That is where R is a real number, like no I under the square root, and also distinct, which probably doesn't mean anything to you yet. But distinct means you got 2 different R values. In other words, you solve the quadratic formula and you got R is 2 and R is 5, which is usually what happens. Remember what happens if there was repeated roots? Remember that was that weird special case, like you got R is 2 and then R is 2 again, right? It's like, oh, you got the same exact answer. Remember that answer was a little bit different, a little bit weird. And so this, in a sense, overdamped would kind of be the normal case. If you just made a random problem up, you're usually going to get 2 different answers. And so this is going to happen when B squared is actually bigger than 4mk. Why is that? Because when you take the square root, then you don't get a negative number, because it's B squared minus 4ac. And so if B squared is bigger than 4ac, or in this case 4mk, then you're going to get a regular number. And finally, the final case, whoa, get back here. Got excited there somehow. Final case is critically damped. In other words, it's right on the edge. And this is where R was a double root, a repeated root. And this would happen when B squared was exactly equal to 4mk. In other words, if that's the case, when you went B squared minus 4ac or B squared minus 4mk, you'd get 0. So it'd be like negative B plus or minus the square root of 0. Like that's how you get 2 of the same exact answer. Okay, let's go play. So in our case, what we're going to do then is we're going to let the mass be 4 kilograms every single time. In other words, let's just stick a mass on there and let's not change the mass every time. And let's have a spring constant that is 9 newtons per meter. So we're using the same spring and the same weight. The only thing we're going to change is the friction part of it. Does that make sense? That's all we're going to change. So for case one, as I said, I already told you in a sense, that means also we need B to be equal to 0. So then you should say, okay, I'm ready to go. Like, you know, and this is on my note sheet. Let me pull this up. Let me see what's on there because I just suddenly remembered this. Rules for solving second order. I think it's this one. So this is the note sheet you have for the next test. Notice a lot of the stuff I just told you is like, that's there for you. You don't have to memorize this stuff. M's the mass, I'm just reading it over real quick. M's the mass, B is the damping, K is the stiffness, F's the exterior forces. Down here it says underdamped. The auxiliary equation, this is how you find that. Let's see, here's something I haven't shown you yet. Yeah, there's a few other things down there we haven't talked about, but it's like reminding you of the basic things we're talking about. So then you would say, okay, well, and this is simple. Like, don't make this hard. In a sense, everything I just told you, you don't need to know in one sense. Like, you can just plug stuff in. If I say, hey, the mass is 4, then you know, you're staring at this equation. You're like, okay, I'll put 4 in for M. Like, that's all there is to this. Don't make it hard. So, okay, 4 times y double prime plus 0 times y prime. And, you know, of course, maybe I'll just leave that off, right? And then plus K, which we said was 9. And notice again, I'm not screwing around with the units. I didn't say 4 grams and like, haha, I got you. You know, it's got to be kilograms. The units are fine. I'm not going to mess with you, and or should the book. I hope they don't. So armed with your, again, maybe you don't even think, this is the undamped case. You just think there is a second order differential equation. Remember, our thinking for this was, hey, if there's some function y is a function of t, then if you will, our guess for this was that y as a function of t was probably some e equation, right? Since if I take its second derivative and I don't take its derivative at all and I add them, they got to be the same thing. Well, e does that, right? I take its derivative and nothing changes, and so fine. But then we said what we saw the other day is it wasn't just e to the t, right? When we did that, it didn't work. But if we stuck some constant in front of it, because when you take the derivative of e to the rt, it becomes re to the rt. We saw there was a way to get that to work, right? And then we said, okay, great. The auxiliary equation here, which is 4r squared, thanks to this term, plus no r, thanks to the missing y prime term, plus 9 would have to be 0. This was the auxiliary equation for that. That's how we found r. Is that all? Like, yeah, that's right. I got that. So, and if you just want to, if you have this in your calculator, I'd recommend just stick it in the quadratic formula every time. A is 4, B is 0, C is 9. Stick it in the quadratic formula, get the answer. However, if you did do that, you need a calculator that will tell you what's under the radical sign, because if it's negative, we're not just saying error and that doesn't matter, right? We need to know what's under the radical sign. However, in this case, you don't have to do that. You could subtract 9 from both sides and divide by r. So r squared is -9/4. Notice I was kind of nice to us here. If you square root that, that's why I picked 9 and 4, by the way, just to make it nice, because you can actually square root 9 and 4. So that would mean, so r is the square root of 9, which is 3, the square root of 4, which is 2, and then there's a negative there, which would produce an I. So if you're using your graphing calculator program, which I don't care if you do, or if you use something online, Wolfram Alpha, whatever, that's fine. That's boring and a waste of our time. Like, you should have known that 100 years ago. What's missing though from my answer that's important? It's not just
The -3/2i.
Yeah, it's actually positive or negative. It could be either one of those. Because if you go back to the, back to this answer here, aren't you squaring it? So if you're squaring it, it doesn't matter whether it's positive or negative. And then, check it out, like go put it in there. If you take 3/2i, remember I squared was -1, wasn't it? So if you square that, you get -1. If you take 3/2 and square that, you get 9/4. Look at that. 9/4 times 4 is 9. The I squared being -1 makes it -9. Look at that. -9 plus 9 is 0. So really that really does work. So as a complex number, you could even think of it as 0 plus or minus 3/2 I if you wanted to. So the real number part of it is 0. And that's because there was no y prime term. And so now what did we do with this then before? Like, it's like, oh no, I got a complex answer. Like I didn't get a real numbered answer. So what do I do with this? You should be looking at your note sheet to kind of discern this, but this was kind of our alpha on our note sheet. And this was our theta. And what did we do with those?
Sine
We
and
got rid of
cosine.
I. Go ahead.
Didn't we use sine and cosine?
That's exactly right.
Yeah.
When you didn't get a real numbered answer, it wasn't just E then. Like our answer E to the RT, it also had a sine and a cosine in it. And again, it was like really complicated how we produced that. So we then said, okay, the format of this answer is a constant times E to the, 0t times the sine of the theta t, and then an exact repeat of the same exact thing, except for with cosine. We saw that it needed both of them. So the theta, and that's what theta is a nice choice, right? Because you think of theta as being like trig. And so that's how, you don't have to have a note sheet to keep that straight, except for what's true about 0e to the 0t, since there didn't happen to be a number in the real number part of the complex number.
Turns into 1.
Yeah, it's always going to be a 1. So I could have, just kind of left that off. But rather than leave it off, I'm just going to say, hey, that's 1. That's 1 too. And so that's our answer. Now, again, you're a little early in this. It might be fun to, and I would recommend you do this kind of thing, but you should kind of have a sense of like, really? You're saying C times sine of 3/2 t plus C2 cosine of 3/2 t. Like if I went back up here and took 2 derivatives of that, multiplied it by 4, and I added it to 9 times no derivatives of that, that would all cancel and I'd actually get 0. Yep, that's exactly what we're saying. You probably should feel like that's magic right now. Like go do it. Don't do it right now, but like you should kind of like, that shouldn't feel all that good. Now we're done now. We're done because we can't go any further unless what?
We have an initial value.
Beautiful. So I'm going to give us an initial value. I'm going to say that y of 0 is 0.3 meters. By the way, I think there's a book problem, and I'm only saying this because of what I wrote as an example. It said I had 30 meters written down. Y of 0 is, 30 centimeters. That centimeters would not be good because we're working in meters. And so if it said 30 centimeters, you'd have to be smart enough to go, that's actually 0.3 meters. You can't trick me. Second is, now, can you tell me what those two things mean in context of this problem? What does that mean you did with the spring?
So at 0, so you started out with the spring 0.3 meters like pulled back towards you.
Yeah, 0.3 meters in whatever the positive direction is. And as I said a second ago, that was to the right. So you pulled it 0.3 meters or 30 centimeters. And then what'd you do?
You just let it go. You didn't put any force to it.
Exactly. You just let it go. You didn't push it while you let it go or pull it even further while you let it go, right?
What number would you change for if you were to push it? With the 0?
The y prime, because y prime is speed, right? Y prime of t is the speed. So, if you have a wrist rocket and you pull it back, that's usually what you do. You pull it back, a slingshot, you pull it back and then you just let go, right? An arrow, you pull it back and just let go. You don't pull it back and then go, and let it go. You'd never be able to hit your target. But you could do that, right? Kid on a swing, you could pull him back and just let go. But you could also pull him back and give him a push while you let it go. Now, remember, there's direction to that. In other words, if you pulled the kid back on the swing and you said that's positive that I pulled him back, but then you pushed him forward, does it make sense that y prime of 0 would be like a negative number because you sent him in the opposite direction? So again, just this should mean things to you in this context. Those aren't just random numbers. It's not just y of 0 equals 8 and y prime of 0 equals 2, and who cares? Let's get on with it. Now, because I rambled away so much of the first part of this class with that beam example, I'm assuming that if I do that, you can solve for C1 and C2. So I'm going to cut to the chase and to just tell you this. Y of t then is equal to, because C1 equals 0, you actually end up with 0.3 cosine of 3/2 t. So it sort of meant that C2 was 0.3 and C1 was 0. So there's your particular equation. This, if you will, was your general equation, and this is now your particular equation. Now you know how the spring is going to behave, and that's kind of cool. Perhaps you remember this from trig. Again, I would say this is kind of unlikely because trig was a long time ago, but do you remember what the significance of that number in front of a trig equation would do? If there's a 5 in there in front of there, what does the trig equation look like? If there's a 10 in front of there, what does it look like?
Shift it out.
Yeah, does it elongate it out?
Yeah, that's the amplitude. Now, because ours is sideways, it just means you pulled it, and notice at time 0, you'd have the cosine of 0, which is 1. Notice you get 0.3. And so
That's
that
the
just means
frequency?
exactly what you said. You pulled it out to 0.3, and then it would go from 0.3 to negative 0.3 to positive 0.3 to negative 0.3. That's what amplitude means. Now you're used to seeing that go up and down, not left and right, but doesn't that kind of make sense? Like that's why the amplitude would be that. What did this number in front of this mean though?
That's your period.
That's the period. Good job. Like, in other words, how long does it take? That's interesting too, right? How long does it take for the spring to let it go, donk and come all the way back? That's one period. It starts here, goes over to there, comes all the way back. That's one period. In the case of the usual boring sine wave that you see, it was like, oh, it's at the top, and then it went down, and then it got back to the top again. And notice that period was typically 2 pi. Isn't that how long it took it to get back to where it started? 2 pi. But that 3/2 messes with the 2 pi. So you may remember that number divided by pi. Is that right? That number divided by pi is the period? No, that's not that.
I think it's 2 pi.
Yeah.
Yeah, that's not right. It's actually 2 pi divided by that number. That's what it is. 2 pi over that number is the period. So what would that be? 4 pi over 3?
I thought it was flipped. I could be wrong. I thought it was 3/2 divided by 2 pi.
You're mixing that up with the frequency.
Ah,
So I'll mention that because I think that actually comes up in a problem. So somebody, I don't have a calculator in front of me. What is 2 pi divided by 1.5? Blurt it out.
4.188.
4.188, so about 4.2. So that basically means it's going to take 4.2 seconds for that spring, when you let it go, to go. Is that fast or slow?
Very
It's
slow.
really slow.
It feels slow, doesn't it? It's like, whoa, really? How could you even get a spring to behave like that? That seems really weird. Does it make sense? It sort of feels like it'd have to be underwater or something, like be in a medium that just didn't let it do what it wants to do. Because I was thinking it was just going to go like.
But wouldn't that be a damping effect? Then our damping effect is 0.
Well, that's exactly right. It couldn't, in a sense, be in. Remember, we're saying this doesn't have any friction, but even air provides resistance. So this is impossible, remember, because this is undamped, which means it's never going to stop. It's just going to go back and forth forever.
Maybe ideal springs just go slower than normal springs. Who knows?
Exactly. Now, it turns out the frequency, this is just kind of interesting, but the frequency is the reverse of that. It is 3/2 over 2 pi. Again, you got a calculator. What's 1.5 divided by 2 pi? Somebody help us out.
2.35.
Yeah, 2.25.
0.25. Is that what you said? 0.25?
2.35.
It's not 2. 1.5 divided by 2 pi. That's not 1.5 divided by 2 times pi. Like if you typed 1.5 divided by 2 pi, you screwed it up.
0.23.
Yeah, you're right though.
It's an easy mistake to make. So 0.23. What would the unit for that be? So this is actually seconds per cycle. If you think about it, like, what do you mean seconds? Well, it's seconds for it to go all the way in one cycle. This 0.23 over here then is actually cycles per second. And that's what frequency means. In other words, that's how many cycles you would get in 1 second. In other words, you're only a fourth of a cycle in 1 second. A second isn't enough time for it to cycle. Well, of course, because it was 4 seconds per cycle, right? So if you flip the period over, you get frequency. If you flip the frequency over, you get period. And do you see how they're both kind of meaningful? One of them is like, how long does it take to get the job done? The other one is like, well, if you only have 1 second, how much of the job do you get done? So those are both useful. That's the real world. That's how it'd be described. The real world, it would actually be frequency. And so if you pluck a guitar string, the frequency is what determines the sound you hear. And so this is really practical and really cool. Now, predictably, I guess I should show you that at least real quick. So notice I typed, and I did this, I made this Desmos to work for any value for M and B and K, but notice if I go back here and I put in what we said, which is a B value of 0. So M is 4, B is 0, K is 9. And so I have kind of a more formulaic answer. So notice it says the Y1 of T, case 1 is 0.3 cosine of capital T. Capital T, notice, is 1.5, 3 halves. And so this is the graph of that. Does that look right? Does that look like what undamped motion would look like?
Yeah.
Yeah, I think it does. I'm going to take a screenshot of it. I can't remember how to take a screenshot. Yes, I can. What are you talking about? It's easy. And again, what I'm of course after is, I mean, I want you to get this class over with. I mean, everybody just, you're in here to kind of get yourself signed off and so forth. And I certainly want you to be able to get that done. But I want you to be able to model stuff. Like, I want you to be able to actually do something with this if you run across this in a job. Remember, if you're in this class, you're probably in it because some program says you need to be in it. Well, if you get in that job, I'd actually like you to, not stink with this.
What
So
real world things are undampened?
yeah, none. Like, actually, I can't think of any because there is friction. Keep in mind, this solves the energy crisis, right? If you could get a spring to do this, all you'd have to do is get a magnet near it and it would actually generate electricity without
Perpetual
friction.
Yeah.
And we would not have a power problem. So this is not possible. If this was possible, that would change society instantly.
So it's friction that's causing the dampening. What if you just go into like a complete vacuum?
Yeah, that would be air resistance. But even then there's like heat. I don't know. I'm starting to like reach the limit of my understanding of physics. Because remember I said I got a C in college and that was a long time ago.
Yeah, there'll be internal forces. They'll be losing some amount of energy.
Yeah, that's right. There's internal. Remember the beam that I was talking about earlier when it kind of was bending, right? And those cells are kind of like rubbing against each other. Well, isn't that happening with a spring? Isn't the metal deflecting too? And so I don't even think it's just wind. I think it's, there's internal forces too. There's heat loss and so forth. Because if you move things, they heat up and then the heat dissipates. And so like that even can have an effect. And so, as I said, I'm floundering here, but notice what makes sense about this. Notice at time 0, remember this is the T axis and this is the Y axis. At time 0, it really is 0.3. And notice it's positive 0.3. It didn't start out down here and go up, right? And then notice it got back to 0.3 again. And it's got back to 0.3 again. Like, that's what undamped means. But what else do you notice about this that fits what we just did? Come on. Here's a hint.
Period is 4.2, like it should be.
Is the period 4.2? Notice it really
Yes.
does look like it is. Notice if you pay attention to the units a little more, wouldn't that be 5? And this would be 4.5. And so, yeah, that really does look like 4.2, doesn't it? So notice it's working. Like this model is actually working. This is an undamped case. So, okay, cool. So yeah, to your point, this isn't very realistic. Our second case. How much time do we have? Oh, we're doing good. We're fine. Our second case, let's let B equal 2. And just as a reminder, I'm going to go back and kind of write in, this was undamped. What was our second case? It was underdamped. Okay, so this apparently is underdamped. I'm warning you ahead of time, underdamped. And of course, we're thinking we don't know exactly what that means. Everything else stayed the same. In other words, it's 4y double prime, but this time plus 2y prime, and it's still plus 9y, and it's still equal to 0 because we're looking at free mechanical vibrations, no exterior forces, no gravity, right? Nothing else pulling on this. And that's why, again, the spring is sideways because it's not hanging down.
The M and the K can be different numbers, right?
Oh, yeah.
4
Yeah.
and the 9. Okay, yeah.
But what matters is what kind of an answer do you get? Remember a second ago, we just got a complex answer. Because of M and K, we happened to get a complex answer. The only thing that made it underdamped is there was no friction, no B value, which causes it just to bounce forever. So in our case, I'm going to stick with 4 and 9 every time, just without changing them. But yeah, solve this. So you should quickly say the auxiliary equation is 4r squared plus 2r plus 9. And you should say, man, that might factor, but I don't want to do it. And again, you're looking for the answer for r so that you can plug it into y equals e to the rt. But remember, you might get a complex number for r, and then you won't be able to do that. It'll be a little worse, like it was for us a second ago. Maybe this time we'll get lucky and we won't get a complex answer.
I feel like if my life could be a sentence, it would be, that might work, but I don't want to do it.
You were the one that wanted to finish that 6 equations, 6 unknowns problem the other day. I think it's the opposite.
Yeah, I wasn't feeling well that day. I don't know what happened.
You weren't yourself.
Yeah, something came over me.
You were inspired, man. The spirit of math came upon you. Again, I'm not going to give you a ton of time here because I want to make sure we get done, but do we get real numbered answers or complex answers?
Complex.
You get a negative under the square root sign. B squared minus 4ac is a negative number. So you end up with r being, and I'm just going to round this off in the interest of time, about negative 0.25 plus or minus 1.48i. So this is just like last time, except for actually this time we did get, well, a non-imaginary term. Last time it was 0. So this isn't going to be quite the same. Why is it not going to be quite the same? It's kind of the same, but why is it not going to be quite the same? What's not going to happen this time? Here's a hint. The E term is not going to go away. Does that make sense? Because it's not going to be 0t. It's going to be like a number. So it's going to have e's and trig in it. So this is kind of the worst case scenario, or at least, we got to do the most work, but like it's the same exact format. Whenever you get a complex answer, you just have e's and signs. Again, look at your note sheet so that you can do this smoothly for a test, because you're definitely going to see this. So then you would say, okay, well then y2 of t is equal to c1 e to the negative 0.25t cosine of 1.48. Oops, I forgot the T. There's the birthday girl. Ooh, thank you. And then C2, exactly the same. And trig, exactly the same, except for sine instead of cosine. And it doesn't obviously matter whether sine is first or cosine is first because you're adding them, right? So there's your, well, we said this is our general equation. I want to go back to the other one and write y1 since I wrote.
Did we use the negative I value?
No, we took away the negative, the fact that, now we didn't take the negative in front of the number, the real number, the 0.25, it came out negative, we leave it negative. But remember, the cool thing about the I thing is we took away I and the plus and the minus by all that ridiculous work we did. And so it's just 1.48. It's not negative 1.48, it's plus or minus, and we just put 1.48 there. So that's the form of our equation. And then we go back and we say y of 0 is 0.3, y prime of 0 is 0, and we get our particular solution. Again, I'm not going to take the time to do that because I want you to, and again, I'm going to round those off. So you actually get like 0.051. Actually, I'll switch that since I wrote the top one with sine first. You get 0.3 for the cosine term. Talk about, I think it's time to be lazy here.
That's pretty lazy.
Are we using the same initial conditions?
Yep.
Got it.
And you get approximately 0.051 for the other term. Again, please stop if I'm going too fast. I have a tendency to get all excited and go too fast. Please stop me. And again, the thing should be like, well, you know, you should be thinking to yourself, I wonder what this is going to look. Why is it called underdamped? And, you know, what's this graph going to look like? Because now it's got not just trig, but it's also got E in it. And then, you know, E is negative here. And so, you know, what's this thing going to look like? You know, you should kind of wonder what's going on. Well, notice for this problem, B was 2. And so I'm going to go back to my.
I'm going to guess that there's not enough friction to stop it, and it's going to go just forever. Is it going to get
Well,
bigger?
That's an interesting hypothesis. I like that. So underdamped, like not enough damping. I mean, I like how you're thinking there. So underdamped. So I changed that, and then I'm going to go turn off the first graph and turn on the second one. So notice that second one is exactly what I just said. Notice Raymond's, I think, incredibly intelligent hypothesis. His hypothesis was going to be that it started at, I think, at 0.3, and then it like went out of control until it sort of broke. And I think that would have made all kinds of sense, that would be underdamped. But in a sense, you know, the physicists, if you will, that categorized this or cataloged it, that isn't what they called underdamped. That's just kind of interesting. And I will say, Raymond, since you brought that up, the reason is because there's no exterior forces. If there was an exterior force like wind, it takes an exterior force to cause something to vibrate out of control and break. You have to have some other force. If there's no other forces, there's nothing I can do with the spring that's going to make it get worse. Like a second ago, we saw it make it back to 0.3 again. If there's no exterior forces, it can't go bigger than that. Does that make sense?
Yeah.
It's a wonderful.
So Doug, there's no like typical spring, right? Because it's either undamped, which is ideal spring, and then you have under, over, and critically. So it's like there's not really like any like perfect spring dampness, right? It's just kind of.
Well, there is, but it just depends on what you're trying to accomplish. In other words, if it's a bike, if it's a spring, because I've told you guys I read mountain bikes, and there's a suspension system for those. Well, see, what I need to have happen if I go over, jump, and land is I need it to absorb the hit instead of my arms and my teeth, right? Is going into the handlebars. And so what they're going to do is they're going to take me from falling at say 20 miles an hour and then going to 0 miles an hour in like a billionth of a second. That's what's going to make me hit my face on the handlebars. Because of the suspension, it's going to take 0.2 seconds to slow me to a stop, which will mean my arms can absorb that. Like that's what a suspension system is doing. And so the question is, how long do you want it to take to absorb that? Do you want it to take 0.1 seconds, 0.2, 0.4, half a second? Like that's what you control if you're the person designing it. Now, if I'm a mountain biker, does it make sense? There's two things to consider. One of them is, how far does it actually compress? But then does it make sense it might uncompress and like buck me off the bike?
Oh, yeah.
So there's a thing called rebound. In other words, it's going to go back to equilibrium. Notice our graph right here. See how it eventually gets back to equilibrium? See how it actually flattened out? It came to a stop. There was friction loss, and so it actually came back to a stop. But notice how long it took to come to a stop. You might say like 14 seconds. That'd be like your car. This is like the Pimp Mobiles from 1960s. It hits a bump and it's like wow, 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 down the road, and like 14 seconds later, that's why it's under damped. You see what I mean?
Yeah.
So,
Okay.
like I need this thing to turn into a mountain bike again and not be going brown, 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 brown for 14 seconds because I'm like 100 more feet down the trail. I got other stuff to do, man. I need that damped more. I need this to get me back to zero faster. I mean, isn't that kind of cool?
Yeah. Okay. I think I get it a little bit more now.
So what do you see right here, though, that you're not surprised by?
Starts at 0.3.
Still at 0.3. What else do you see that's kind of interesting? What's the period of this graph?
Somewhere like around 4.2. I don't know if it is exactly though.
Yeah, it's kind of around 4.2. And then that sort of feels random. Let me show you one thing in the, actually get a copy of this onto the note sheet. What happened? Brought the wrong picture in. At least I noticed it. So, as one of you pointed out, it's still at 0.3. That's good because that was our initial condition. But then notice its period still appears to be, well, let's do a little better. Is it actually 4.2? This would be 4.2. So notice it's a hair past 4.2, but it doesn't make it to 4.4. So I don't know, 4.25. I don't know. I actually don't know. Is that a coincidence? And by the way, do you think that's still 4.2 if I go out to the next peak? If it was, wouldn't that be like 8.5? Do you agree with that? Would the next peak be about 8.5 if I double 4.25?
Maybe one of the E's kind of stretches it out over time.
Notice the period isn't screwed up. Like it actually, the period is intact. See how at about 8.5, it really is back to the peak again. So it actually has a constant period, which is kind of cool. And I showed you this quickly the other day, but it turns out like this is the E effect right here. I won't draw this in, but like this is the E to the negative 0.25 T. That's if I graphed Y to the E to the negative 0.25 T, again, I have to put a certain coefficient in front of it that I have to actually calculate. But that's exactly what's dampening it is the E. The E is what caused that thing to lay down. Notice the fact that it was negative was real important because that's what negative E looks like. Positive E looks like this, but negative E looks like that. So it is that's doing the dampening, but it's just not fast enough. That's kind of the idea. That's why it's called underdamped. It isn't slowing it down fast enough. So that's kind of interesting.
So Doug, we talked about your mountain bike and we talked about the need for like more damping, otherwise you're just going to go out of control. How do you dampen a spring?
In the case of, that's a wonderful question. Do you know what they do inside a mountain bike? They actually fill the chamber with oil. In other words, the spring is sliding through a liquid. So that's what old people do for aerobics, right? They get in the pool and they do aerobics in the pool because the pool provides more resistance. So if I'm going like this in the air, it's like, oh, that's really easy. But do that in water, not easy. And so you can damp it by putting a viscous fluid inside there with it. That's kind of cool, isn't it?
Yes, that's why your spring has like a hard rubber exterior on the spring, because inside there's oil in it.
Yeah, so you got to have all these, you have to have these gaskets that keep it from escaping, because as soon as it escapes, you're in bad shape.
That's bizarre. I never knew that.
I don't know if we'll have time to talk about this, but I'm just going to mention it for now, and we'll see if we run out of time. But notice this equation right here does not have a sine and a cosine. You notice that? It's like, what? Well, there is a way to combine them. In other words, the equation I just gave you that had E sine of junk plus E cosine of junk, you can combine them into just one sine equation. And this is how to do it. Notice the thing you don't know here, like you know everything. Didn't we say that was negative 0.25 and this was 1.48? Well, what's this guy right there? What's that? Well, notice there it is. There's a formula for it.
Is that phi or rho? Which one?
The
Greek name for that?
Let's see, that's phi for phi, PHI, yeah.
Okay.
Rho is more like a P. It sort of looks like a P. And because of the text, that's kind of weird. Usually phi looks like that. So I think, I'm actually not 100% sure because that doesn't look very good.
I'm pretty sure it's a phi. I think it's just written weird.
I think it's a weird font for phi, yeah.
Yeah, I've seen it written like that.
So remember our numbers though in front were, what was it, 0.051. And then it was 0.3. Well, notice if you combine those two numbers right here, there's the 0.051 and there's the 0.3. If you do the Pythagorean theorem to them, then you get a brand new amplitude, if you will, in front of that. That's kind of cool, isn't it? And if I wanted to graph that E that I was telling you dampened it, that's exactly the A I would have to calculate. I'd have to take the square root of 0.3 squared plus 0.051 squared. And then if I graphed just that number E to the negative 0.25t, it would lay perfectly against that graph. And you'd be able to see, oh yeah, it's the E that's causing that to dampen. And so does it make sense that what I need is an E for my shock? I need an E that doesn't do this. I need an E that does this. You see what I'm saying? I need this to be done shocking me after like 1 second so that I can get back to mountain biking and be ready for the next hit, right? Does that make sense? So that's kind of cool. Okay, third case, which is overdamped. The overdamped case. And so this is going to come to a stop too fast. I guess you might, doesn't that seem right? In other words, like instead of taking like 0.2 seconds and giving me a nice, gentle recovery, it's like 0.01 seconds. Like it is damped, but it's like way too fast. And so in this case, if I just change the B value to 20, and notice that's a bigger number, right? Remember, these are friction numbers. It was 0, none, then it was just a tiny little 2, which wasn't damped enough. And so it kept on going for 12 seconds. Well, if I say B is 20, now it's got like a massive number for friction, right? So again, in the interest of time, I'll go too fast here, but we left the mass alone. We switched B to 20 and we left the spring constant alone, and it was still a free mechanical vibration, no exterior forces. Well, what do you get this time when you put that in the quadratic formula? There's crying grandchildren out my door. Do you guys hear them?
Only barely.
So we get two definite numbers.
Yeah, you actually get non-I numbers for the first time. And, I find myself going, thank God, like this is not weird anymore. You get R equals -1/2 or R equals -9/2. Now I'm going to erase this, but you could say -1/2 plus or minus 0I. Every number is a complex number. It's just that 0 is the coefficient in front of the imaginary part of that number. But, we would just say, well, why would you put that there? Correct. You wouldn't. So now, of course, we can say, well, great, this is way easier. I don't have all that ridiculous sign stuff that was involved in it, making I go away, right? That's where sign got involved because of that cool expansion of E, that Math 253 expansion of E, another way to write E, and it's like E can be replaced with sines and cosines. And oh my God, that's just crazy that brought up. But what we find here is that no, actually the third equation then as a function of T is just C1E to the, well, pick one of them, -1/2 T, and then C2 E to the -9/2 T. Of course, we don't care if those are decimals, that's fine. And then you go back to the same initial conditions and you get y of 3 of T, the particular solution, because I already calculated this ahead of time, is 0.338 E to the -1/2 T. And C2 is actually -0.038, really small coefficient. So that kind of makes it minimize the effect. So that would be our model this time. Notice there's no sign. What do you think's going to, wait, there's no sign. What did sign do to the previous two problems? And then what's not going to happen now? If I don't have a sign, then what's the graph going to look like?
Pretty steady.
It's not going to have that bounce up and down, right? The bounce up and down thing happened because of the sign, and there isn't one of those now, right? So
It's not going to be oscillation.
yeah, you're not going to have that oscillation to a stop. And so I go back here and throw in B is 20, bam. And I go down here and turn off that one and turn this one on. And again, you don't see the -1/2, you see capital A plus capital T. But you may notice up above, capital A is the -b/2a part of the complex number. And the capital T part is the square root of b squared minus 4mk/2m. And so if you take a plus t, -2.5 plus 2, you actually do get -0.5. And so again, I was just saving myself a bunch of time, right? That's what algebra is for. I didn't solve one problem, I solved them all. Okay, well, look at this. What are you not surprised by? Again,
Starts at 0.3.
starts at 0.3. What are you also not surprised at?
Goes to 0.
Goes to 0 because it's got to stop, right? If it's got some damping in it, it's not going to, be up there forever. But think about this. What happened? If you pulled the spring back and you let it go, what did it do according to the graph? Yeah, it just went like it never even oscillated. Do you see why that would be called overdamped? Can you appreciate if you had a pretty weak spring and it was in a liquid and you let it go, that it would just kind of go come to a stop? That would kind of happen, wouldn't it? So you can kind of see why this is overdamped. Now, if I'm a mountain biker, I still think 8 seconds is too long, but it didn't allow for any oscillation. That's kind of what happened. It takes a complex value for R to actually produce oscillation. As I said the other day, isn't that amazing? Because most springs or, a tree in the wind is going to kind of wave back and forth. It doesn't wave back and forth unless there's a complex number. Isn't that crazy? Now, is this unrealistic though? No, like you might not want something to oscillate back and forth. You might just want it to work its way back. Now, if I said, if you're the bike designer and you said, okay, well, that's, pretty much back to 0 after 8 seconds. So I went off the jump and the bike compressed 30 centimeters and then it took 8 seconds for it to go back to normal. You might say, nah, that isn't going to work. Well, what are you going to do? Well, then you're going to damp it. Well, even more, maybe 20 isn't the right answer. Does that make sense? Maybe it should be 40 because I want it to be back in 1 second. Well, you can appreciate, you could probably get it to do that, couldn't you? And that's your job if you're an engineer is to come up with something that would actually dampen it in that way. So that's kind of fun. The kids were crying and I had like 0.5 seconds to do this before class. You may notice my coefficients there are numbers, not letters. So I didn't have time to make formulas out of those because I'd love to go back and change that 20 to a 40 and look at the graph again, but I have to recalculate the constants and I didn't have time to recalculate, like make a formula out of them. So stuck with that. You got my, didn't get my A game, you got my B+ game.
So Doug, in 253, we had all those rules of convergence and divergence. Do those apply to situations like this if the spring is going to oscillate to infinity or converge to a value?
Yeah, that's exactly right. In other words, does this graph converge to 0 in kind of a, an appreciable time? That's the cool thing about a spring is the spring is going to go to 0. If it's got any damping at all, it's going to 0. It's just a question of, how quickly is it going there? So yeah, that actually totally applies. So I'm not surprised to see 0.3 again. And I want to just point out no oscillation. I don't know how to spell oscillation. Is it got 2 L's or 1? We have enough time to look at our 4th case, which we said was critically damped. That's kind of interesting. Critically, it's like critical. Critically damped. So let's let B this time be 12. So this is like 20 was too damped. And so, I was like, oh no, I want it to oscillate some. And so let's take it back to 12. Like, why 12? Why not 10? Why not 13? I don't know. I'm just picking 12. Okay. But watch what happens if you pick 12. It's really interesting. 4y double prime, not changing the mass. 12 times y prime, not changing the spring constant. So what happens this time? Because your auxiliary equation happens to be 4r squared plus 12r plus 9 equals 0. What happens this time?
They're both equal to the same thing.
You get the same exact answer. You end up with 2r plus 3 and 2r plus 3 if you factor it. You end up with negative b plus or minus the square root of b squared, 144, minus 4 times a times c over 2 times a. But it's interesting what happens. What happens here? And I said this on my original note. What did I say happened originally back there to this particular case? The b squared is exactly equal to mk. You get 0 under the square root. And that's what happened. That's what happens in this case. But again, I want you to be thinking like, why is that called critically damped? So now again, you might be saying, I don't see 2 answers there, right? Didn't the 2 answers come for the plus or the minus? That's why I'm taking the time to write this out with the quadratic formula. Well, that's because there's not 2 answers, there's 1. But it's important to know that it's a repetition. Notice you get the same answer as above. Negative 12 divided by 8 is negative 1.5. If you have 2r plus 3 equal to 0 and you solve it, you get negative 3/2. So it's very important to recognize when you have a repeated root. So r equals negative 3/2 and r equals negative 3/2. It's no reason to write that down, but you definitely need to notice that's a repeated root. Now looking at your note sheet, pulling this back up from before, because you should not remember this, like you should be leaning heavily on your note sheet. What do you do if you get repeated roots? Notice it says real, not complex. real roots, no I values. What do you do? What's the format of your answer? You see how you better be paying attention to your notes? Like we've learned way too much to like hold this in your head, right? What do you do? Notice there's only one E, and so it's, you know, -3/2. But what do you change?
You add the T after the second constant, C2.
Yeah, you add that T in there. And remember, that was kind of what we did down here too. When there was a repeated root, you added another T. Like this was the same larger pattern. So anyway, you got some stuff to study here, right? Like I'm explaining this quickly as though you're good at it, but it's like I showed you this once. You're not good at this yet. You really need to slow down and practice all this stuff. So that means then that we can say that our equation, the fourth equation, is C1e to the -3/2 t, but then plus C2e to the -3/2 t, which would be dumb. If you just wrote it like that, that would make no sense at all because they're the same exact answer. But there's a T in front of this one. So there's what our answer looks like. It looks like that. Notice no trig, which means there's no oscillation again. I wonder what this is going to look like. It seems kind of like, well, isn't it going to look just like before? Again, I won't take our time because we don't have enough of it to solve for C1 and C2. But if we go back and put those initial conditions in, and by the way, those initial conditions are going to be a bummer, remember, because you got to take the derivative and so forth. I'm blowing past a lot of work here. Like you should go redo everything that I'm doing, but actually do it. If you want to get this stuff, it takes practice. Listening to me is not enough. You end up with 0.3 e to the -3/2 t. In other words, the C1 is 0.3, but you get 0.45 for the other one. So there's your equation for critically damped. Again, I want you to be thinking like, why would that be critically? Why is it critical? Why is this like such a just, oh man, what's critical about this? Let's go look at the graph. So if I put 12 in for this,
Half expecting just like no movement.
yeah, isn't it kind of like, what in the world must this do? Now, part of you should say, that's the same graph we just saw. But what's different about it? It still goes to 0.3, right? But what's different about it?
Is it not leveling off at 0? Does it like stay right above it?
That's a good question. Well, they're all leveling off at 0. So that wasn't different. But you know, if I zoom in close enough, has it made it to 0 here yet? The answer is no. I don't know if I can zoom in enough on this to show that, but you know, after 44 seconds, it's close enough, right? Even if I am able to zoom in and it shows it's different, it's close enough, right? But notice the Y values right now, 2 to the times 10 to the -6, that's 0.00002. Like we're really close right now. So for all intents and purposes, it is not there yet, but it's, you know, plenty close enough. But what is different than last time? It's still on its way down to 0, but how did it get there?
It looks flatter maybe. Like it's kind of shooting down to 0 in a diagonal line more than a curve.
Yeah. How long did it take to get there before? You know, again, it never gets there, but how long did it take before it was pretty much there?
Oh, was it 8 seconds?
It was like 8 seconds. And notice this time it's like, you know, again, it's debatable, but it's like 4 or 5 seconds. It's pretty close.
That's a road bike spring right there.
So notice what's interesting is that's still too long. Like if I'm a mountain biker, that's still kind of not enough. Now, what does that mean? Does it mean it's impossible to get it to fix it? No, it means you need a better spring. Remember how we put 9 in for the spring constant? That means you need 19 or, you know, 72 or like some stronger spring. Like this can't do it. It's too weak of a spring. You can't get a weak spring to, you know, get you there. That's the idea. So remember, there's other things you can change. How much does the mountain bike weigh? That's mass. And then what size spring did you put in there? So we chose a spring, and it's just not a spring that will get the job done. Why would this be called critical? What's so critical about 12? Like what happened there?
Well, the square root went away.
The square root went away.
but
You're
I don't know
barking
if
up the
I'd-
right tree.
I don't know if
You're-
I'd call that critical.
You're barking up the right tree. Keep thinking about that, whole class. This is a really interesting. It's a very interesting point. Like if you guys get it, great. But even if I tell you, you're like, oh, that makes total sense. It's totally cool.
So we have no sine cosine because of the square root going away.
Also barking up the right tree. What does it take to get a sine and a cosine?
A degree.
It's
An angle?
the point in between where you would get a sine and cosine, right?
Didn't want to do that.
Oscillation.
Do you notice right below, let's go there. Do you notice that's what's under the square root sign right there? B squared minus 4AC. Notice it came out 0, right? In order to get a sine and a cosine, what does that number under the square root have to be?
Has to
Somebody
be-
save us. I'm not telling us. How come those first two examples had a sine and a cosine and this one doesn't?
has to have a negative under the square root.
It
Imaginary
has to
number.
have a negative under the square root, right? The I value showed up and that's what caused sine and cosine. Well, notice, what did we get under the square root? 0. That's as close as you can get to a negative without getting one. You see what I'm saying? If you got under the square root like a 27, well, then you're a long ways from getting a negative number. The square root of 27 is, 5. But if it's the square root of 20 and then 12 and then 6 and then 4 and then 1, ooh, we're on our way. Well, if that had been not 0, but negative 0.1, does it make sense we would have suddenly had a sine and a cosine? So that's why it's critical. This is as close as you can possibly get before it starts oscillating. If you damped it to 11. No, over damped. Is that right? Do I got to take it up or down? Do I go to 11 or 13? Thinking out loud, I don't know the answer.
I think it was like last when we had the smaller one, it was underdamped.
Yeah, like it was 20, we got real answers, and so it's 11, isn't it? Notice what's under the square root sign? A negative 23, and so now we're going to get sine and cosine, which means this is no longer the correct graph. Now, what would have been cool, as I said, is if I had calculated C1 and C2. Unfortunately, I can't show you what that graph looks like. But that just caused I, because there's a negative there. And notice I just chose 11, and yet it was way negative. It wasn't just like negative 0.1. Does it make sense I could have chose 11.9? Now it's the square root of negative 2.39. So the idea is if you dampened it, if you changed the damping, if you damped it a little less, then it's now going to have the strength to oscillate a little bit. So it would have made it, if you will, below the x-axis. It wouldn't have just went from 0.3 and worked its way as quickly possible to 0. It would have started at 0.3 and got underneath the axis a little bit and oscillated a hair. Now it still would have leveled out really fast. Does that make sense? But it would have actually made it past 0 and went past it and then came back to it. That's why it's critical. It's like the line between oscillation and not oscillation. Is that kind of neat? Doesn't that sort of make physical sense to you if you think about it? That's kind of cool, right?
That is cool.
So you can kind of see why these are named this way and so forth. But I would put you a little bit at ease in the sense that on a test, I just want to be able to, I just want to be able to say, okay, we're going to model a spring now. And I'm going to say effectively mass is 12. The, spring coefficient is 18 and the damping coefficient is 16. Like go find a model for the spring. I mean, if you can solve a second order differential equation, you can do this. Like that's all you're doing here. It's just a creative way to give you this. But again, if you take a class like this and you can't do anything with it, then you're wasting your time. I mean, yeah, you're getting your degree and you're getting a job, but wouldn't it be cool if you could actually go design a bike suspension? And you can see that this would get you there. Like it's your first introduction. Remember 2 hours ago, you didn't know any of this. So you've made a lot of progress in 2 hours, but if you spent more time with this and, played around with it more, you can see that you could actually start to be able to do something with this. Isn't that kind of awesome? So still went through the 0.0, 0.3. And if B was any smaller, in other words, a little less damping, then it would have oscillated. It would have oscillated. So it might have went, like this, and then it went. It still would have got there quickly. But it might have looked something like that. So what I can't remember is whether in your assignment they want you to go to the trouble, and I just want to kind of say this out loud, and I'll leave it at this. I don't really care as far as because of the fact that you can graph it, you don't need to collect everything together into one trig expression. So the ones that did oscillate, the good thing about collecting it into one trig equation like this is, well, notice this number doesn't change, theta doesn't change, but this shift right here, you may remember that's a shift of the graph, a little bit left, a little bit right. You can know what that shift is, and then you can know what the amplitude is, and you need this formula to know the amplitude. So this is basically the amplitude, and this is the shift. And so if somebody wanted to know about the amplitude and the shift, you would have to put them together, because you have to look at both amplitudes. You can't look at one. A second ago, we got 0.3 and 0.45 as the coefficients, and those didn't have sines and cosines, but it's like, oh, what's the amplitude? One is one number and one's another number. Well, you know how to do that now. You take them, square root them, and add them together. So there is a way to kind of collect it. I just can't, I don't think on a test I care whether or not you can do that, but I can't remember if in your assignment you do care. So that's kind of cool. Let's see. So as a reminder, today is Tuesday. Tomorrow is we're meeting at 12:30 day, because I am flying home at 7:30 in the morning. I'm landing at 11. I'll rip home, figure out what we're covering tomorrow. What are we covering tomorrow? We're covering the same thing, except for what do you think we're doing different?
Probably adding that constant on the end.
Yeah, we're going to have some external force added into it. And what's really kind of fun is there's all kinds of external forces to add. In other words, you could just have gravity, which is just a constant number, added to it. Or you could have something really varying, like a parent pushing a kid on a swing, right? Like you don't just pull them and then let them go walk away. You could stand back there and be like, oh, I'm just going to keep adding energy to the system so they can keep swinging. Well, that's an external force. Or you could be wind blowing on the Tacoma Narrows Bridge that causes it to spiral out of control and ultimately break. Or the kid on the swing, you could push harder and harder until they start going all the way around. That'd be awesome. So your force can be something that you time, and that's what happened with Tacoma Narrows, by the way, is the push of the parent on the swing. If that happens at the right time, it makes the kid go higher and higher. But what if the kid is swinging back towards you and you push right when they get to the bottom? What happens? Their neck snaps and they die. Like you can't push at the wrong time. Does that make sense? You got to push at the correct time. But if you push at the correct time, they go higher and higher and higher, and then the bridge breaks because it spirals out of control. But if you push at the wrong time, if you blow at the right time, that could actually fix it. That's the idea. Now, a bridge doesn't have a neck, but if it was swinging wildly and you pushed at the right time, wouldn't that bring it to a stop? And so I mentioned the other day that in the top of skyscrapers, which are really lightweight now because they're cheaper, they tend to like sway in the wind, and it's amazing how much they sway. I'm talking many feet back and forth. And so what they do to stop that is they put a huge block of concrete up in the top floor of that thing. And when this thing is wanting to blow back this way, they turn on the motor, if you will, and push the concrete against it. They damp it. Isn't that what you do with the kid on a swing? You're like, okay, it's time to stop now. And so then you don't just jam them stopped at the bottom, but don't you you push as they're coming towards you, but kind of lightly so that they'll, dampen. That's the design between a mass, I think it's called a mass tuned damper, But notice the word damper is even in that statement. Go Google search that after this. It's really interesting if you want to see it. But it's like you can control whether something oscillates or not by adding an exterior force at the right time. You can make it go higher or you can make it come to a stop if you rhythmically apply kind of an exterior force. So the exterior force could be a sine wave where you apply, a burst of push every 3 seconds, and they'll bring the building to a stop. And so brilliant, who thinks of this stuff? And it's like that's the application of all of this. All right, as usual, I've gone over. As it says at the top, stop sharing. Stop sharing. You're oversharing.
Thanks, Doug.
Thanks, Doug.
Thank you all. We'll see you tomorrow.
Travel safe.
I will. I'm going to be in the back and not have any idea who's playing this thing.
See you tomorrow, Doug.
Okay, real quick, I just had a question about the homework from last week.
Mhm.
Well, I can share my screen, that'll be easy. And you can just keep eating your burger or,
Whatever the heck that thing is.
yeah. So here, I think I was misunderstanding how to use the formula. Because my answer has this extra term, and I think I just messed up solving for the R.
So you got R values of, whoa, come in here. You got R values of negative 0.45 and 1.5, so that makes sense. And then notice your polynomial in front of your e to the t at the top. It's t to the fourth, which means you need a fourth degree polynomial. So you did that. At to the fourth, and then everything below it, bt to the third, ct squared. And then what's that last thing?
The T out front.
Yeah.
So
When do you do that?
okay, yeah, I see that I messed that up. This should have become a 1 because the S was 0.
That's right. S was 0. So basically it's saying don't add it.
Okay,
When do you
so
add it?
when S is greater than 0?
Yeah, when is that though? According to the note sheet, like when do you do that?
I'd have to look at the note sheet again. All of this stuff is in the way.
I'll pull it up. Oh, I guess you have to stop sharing, so never mind, I won't.
Okay.
You pull it up. I want you to look at it.
Oh, for roots. So R wasn't a root because it was imaginary.
Yeah, so go back to your thing. Do you see how the original problem was e to the 1t, right?
Mhm.
So that was e to the 1t. And what you discovered is your two roots weren't ones.
Okay. Yeah, that makes sense. And that's why you just have the e to the 1t out front.
Now, the other thing that's not true is, like, in order for your guess to be correct, you don't put those R values of negative 4.5 and 1.5 in there, because if you took the derivative of those, you're not going to end up with an e to the t. You need to end up with an e to the t. So those should not be e to the negative 4.5t and e to the 1.5t. They should just be e to the t. And there should not be two of them, just one. Again, look back at the note sheet and notice the roots are not what's up there. You only check the roots to make sure they don't match. Now, what are the roots for? They're for the auxiliary part of the answer,
Okay.
if that makes any sense. So the larger answer to this question, the answer that you're guessing will just produce the t to the fourth e to the t. But remember, on what's on the other side is also that plus 0. So that means the homogeneous answers are a part of it too. So your answer is really just a t to the fourth plus bt cubed times e to the t. That'll take care of the t to the fourth e to the t. But then plus C1 e to the negative 4.5t plus C2 e to the 1.5t. That'll be the homogeneous answers that get added to it too. But in this problem, you're just determining a guess that will produce the t to the fourth e to the t.
Okay. Yeah, that makes sense. And I'm definitely gonna review this stuff because these were really difficult. And then I got this one, I included my e to the 4t. Is that wrong just because I don't have a 4 up there in the original?
Yeah, that
Okay.
original one is e to the negative 3t. So that's all you should have is e to the negative 3t's.
Okay, yeah, that answers that.
But notice when you check the auxiliary equation, -3 was one of the answers this time. It's like, oh, it's a match.
Okay.
So, what do you do because there was a match? Well, now you're right. The t to the 1 in front of that did need to be there.
Okay. Yeah, that makes sense. And then is there a test this week?
No, I don't think so.
Okay.
According